question of the day. I'm Professor Q, so glad to be with you. So, what is the question of the day? I was thinking as I was driving along, have you ever wondered how birds could actually be sitting on an electrical line and not being hurt at all? That is just a wondrous idea. Well, what do you think? Well, inquiring minds want to know, how is it that those little birds are able to be safe while they are sitting on a wire with electricity flowing through it? It all has to do with being grounded, because those birds have both of their feet on the wire, and electricity takes the line of least resistance, and therefore the bird's legs have what you call electrical potential energy. So as the electricity is running through and the bird's not grounded, the bird is safe. Isn't that amazing? Now the question is, what happens if that bird decides to take a sidestep to the other line while it has one leg on one line and one leg on the other? Uh-oh, sounds like that little bird actually completed a circuit. And we'll talk about that in just a moment. Okay, I have another quick question for you. Since we're talking a little bit about electricity today, how many electrical grids are there in the United States? There are 3 electrical grids that exist in the United States. There is the Eastern, Western, and you believe it, Texas interconnection. Isn't that amazing? So, talking about all of this electricity, could we even live without it? Absolutely not. In fact, I even have my electrical component right here, just like almost everybody else does too. So, what is electricity? I think you're right. Electricity is actually the flow of electrons that helps to be able to produce light and energy of different forms and also in motion. So I have a little special guest here to help us out with some further exploratory experiments all about electricity. Luigi! Oh, Luigi! Ah, there's Luigi right here. Say hi, Luigi. Luigi, of course, he's my favorite light bulb of all. And he's going to help us as we go along figuring out information about electrical circuits. Because if the electrical circuit doesn't connect, he does not get a bright idea. So, my question is, well, where do electrons come from? Atoms, you say? You're right, because atoms are made up of protons, neutrons, and electrons. And what charge do electrons have? Negative. Well, let's not be so negative, but yes, they are negative charge, right? And so those negativities will help to be able to push those electrons along to be able to help the flow and make a connection so light can happen and movement can happen. So let's talk a little bit more about how are many ways that one can light a light bulb. So here's a Luigi, but I'm going to get Luigi's cousin, okay? So Luigi's cousin is right here. And so we have a light bulb, a battery, and we have wires. So have you ever wondered, how many wires does it take with a battery to light a light bulb? At this time, I'd like for you in your interactive science notebook to please go ahead and write down what your prediction would be. Once again, how many wires does it take with a battery to light this light bulb? Go ahead and think about it now. So, did you think a little bit more about that inquiry question regarding how many of these wires and a battery will it take to be able to light a light bulb? Well, I wanted to be able to explore a little bit more with you and talk about, well, what we have here. So I have a battery within a battery holder where the wires, how many wires do I have? I have 2, that's right. And they're connected to the Fondstock clips. And I have a bulb holder here with the bulb. So I've connected the 2 wires to the battery and the bulb holder. And let's see, do you think it's going to light when I twist the bulb? Let's find out. 1, there it is. It did light. And how many wires did it take? It took 2. But wait a minute, Professor Q, you said just with a battery, a bulb, and wires. You're so right. So let's try that out then, shall we? Let's go ahead and extract both the battery holder and the bulb holder and see if we could possibly light the light bulb. Well, here are 2 wires, and I'm going to see if I could just crisscross applesauce the wires and put them on the bottom terminal and see if it needs 2. All right, I'm going to put them together here. Are you ready? 1, 2, 3. What? It didn't work. What happened? Wait a minute. Are you saying that I need to add something to the top terminal? Okay, let's try that. Then maybe 2 wires I will bend and see if they'll work on the bulb. All right, I'm going to put the bulb on the positive terminal and let's see. 1, 2. Uh-oh, I saw something happen. 3, it worked. I have 2 wires to light a light bulb. You're so smart. But I challenge you one more time. Do you think you could do this activity with less than 2 wires? Let's find out. All right, I'm going to take 1 wire away. I'll keep this one on the bottom. Drum roll, please. Okay, here we go. I'm going to connect the bulb and it worked! Oh my goodness! That was a great bright idea that you had. Wow! You're lighting up my world. So, the question is, taking a look at this diagram, I'd like for you to please go ahead and illustrate what this looks like in your interactive science notebook at this time. We'll go ahead and pause the video now. Wow, isn't that wonderful? Look at that bright light. You know what? That makes me have an idea. I think we should ask Luigi, don't you? Hey, Luigi, what do you think? Do you think that there is more than one way to be able to light this light with only 1 wire and 1 battery? I think we should try to give it an opportunity to see if we can. All right. So I think we might have a special guest. This is Rocky. Say hi, Rocky, to everybody. He has bright ideas all the time. He's going to help us out today. Thank you. All right. So my question is then, I'm going to place this bulb on the side. And do you think it's going to light? Make your prediction. 1, 2, 3. It did not. Oh my goodness. please quickly draw what this looks like. All right, Luigi wants us to try a different way. So let's try a different way. So as you see that we have on the top positive terminal, there is this plastic coating and then we have the metal. So let's try putting the bulb on the plastic coating and seeing if it would actually light. Let's count down. 3, 2, 1. Oh, it did not light. Oh, but you know what? Let's try it right next onto the metal. Because the first time we put it where? You're right, we put it right on top. But will this be able to light up on the metal part? What is your prediction? All right, here we go. Countdown. 3, 2, 1. It did! Oh my goodness! So what do you think is the commonality between being on the top as well as in the bottom? And what was it? And what is it, could you say, that causes it not to light on the side? With the person next to you, or think about it, what is it that causes this electrical circuit not to light? So I asked you, what do you think caused the light bulb not to light when we were discussing that light bulb being here on the side of the battery? Well, let's further explore that thought as well. So I have some items here and I have this set up and we're going to determine what that could possibly be. So think about it for a moment. What is it called in science about electricity that allows electrons to flow? You're right, conductors. And where do students normally hear the word conductors? Woot, woot. That's right, it's a choo-choo train, right? Students are very familiar with that. Or what about the symphony? Who's the person who's in charge of directing all of the musicians and instruments? It's the conductor. Well, that allows a conductor allows electricity, the electrons, to flow in a circuit. Well, you know, I keep bringing up this idea of a circuit. Well, what does that mean? Well, you remember when I actually had the battery, the wire, and the bulb, that it kind of almost made a circle. And in that sense, it was to be able to light the light bulb. So a circuit is resemblance of a circuit, of a circle, where electrons will be able to flow throughout. So here, when we have an item, we need an item that will help us to be able to continue the flow of electrons. So what type of items would that be? Well, let's explore, shall we? Okay, so here's our setup. Are we ready? 1, 2, 3. What do we have here? We have a nail. What type of nail? Metal, you say? Well, let's find out. Will metal allow the electrons to conduct? Let's see. Oh my, you are so right to be, because this metal is allowing the electrons to flow, and it's flowing from one side to the next. Okay, so let's put this over here, and then our next question will be, well, what about this? What is this object? You're right. It's a golf tee. And what is this object made up of? Wood. Well, let's place it as well and see. Will this tee it up and let the electrons flow? Let's try. 3, 2, 1. what happened to the electrons? The bulb did not light. So apparently this T stopped the electrons from flowing. Well, let's put that over here and we'll categorize. All right, what do you think? Make your prediction. This is a paper clip. What is a paper clip made up of? Metal. What else was the wire made up of? Metal. Do you think this is going to be a conductor? All right, let me put this here. Let's test it. 3, 2, 1. It did. You're so right. How smart you are. Okay, well, let's try. Shall we? A straw. Can't live without straws, but what is a straw made up of? Oh, I think they're made up of plastic. But lately there's been some paper straws out there too. But let's find out. What will a plastic straw do? Here we go. It did not light the light bulb. Well, let's put this in the category with the T. But yet we have two different components altogether. What about this marble? Oh my goodness. What is this marble made up of? Some particular type of plastic or maybe ceramic, you say? All right, we'll just insert that. Do you have your prediction yet? Okay, here we go. 3, 2, 1. Nothing. Oh my. Professor Q, what is going on with you? Well, we have 3 distinctive types of objects that are not allowing the electrons to flow. What do we have here? We have like a bolt that we are going to work with. And it may be some type of metal per se. Well, let's see on the count of 3. 1, 2, 3. There's the light. Oh my goodness. Okay, well, let's take a look. What are the similarities and what are some differences? Well, we have over here that each one of these has what component that is common? Metal, you're right. And over here, what do we have in common? Well, the commonality is that they're not allowing the electrons to flow. So what can we infer? I think we can infer that metal is a conductor. But then again, what is it called? That does not allow electrons to flow. Wow, my goodness. Have you ever had a coffee cup? Did that coffee cup make that coffee or drink of soda either hot or cold? It kept it at one of those temperatures. Well, what we call that is an insulator. Say insulator, that's right. An insulator keeps things in. So that insulator stops the electrons from flowing. I say insulator, you say stop. Insulator, insulator, insulator. All right, wonderful. So now we are having a better, thorough understanding that we have conductors and insulators and electricity. Are you ready to explore further? So am I. Oh my goodness, I'm entangled in all of these lights. I just can't seem to find the one that burned out. Does this just drive you bananas? It does me. Why can't we find the one that burns out? It's just one all over the place. Oh my goodness, what can we do? Luigi, we need you. Luigi, what do we need to do? You say what? You say series? Check the series circuit? You say? Well, let's find out. Okay. So, Luigi says this is a series circuit. So what's a series circuit? Well, let's find out. Are you ready to play? All right. Let me get untangled just a moment and I'll be right back with you. Now that I got untangled out of that mess of lights, let's talk about a series circuit. So, where have you heard the word series before? Oh, stop binge watching all those series that you always like to see. Now, oh my goodness, my Texas accent's coming out. Yeehaw! All right. Well, let's talk about this now. Must be them cowboys and who knows what type of series I've been watching these days. So, we have, as I mentioned earlier, about a circuit. And I just wanted to recap that real quick. As you see, this is evidence of like a circle where you have the electrons that will be flowing in a direct conventional current flow. And so when I connect, the current is flowing of electrons. Okay? But now, the question I have is, well, what if we add more lights, like that string of Christmas lights? What does that look like overall? Well, let's focus over in this area where I've given you an example. Now, I do have a couple of extra batteries here, and we're talking about a battery. How many volts is this battery? Well, that's a good question. What is voltage anyway? Well, voltage is the ability for pushing through those electrons. That's right. Voltage is pushing through electrons. Liken it to that of water being pushed out of a water hose. Just forces right through. So that's when all those electrons are getting close to each other, and guess what? Because they're both negative, they repel one another. Have you ever heard similar types of charges do what? They repel. That's correct. So, as we're moving forward here, so if I have the voltage, oh my goodness, it's 1.5 volts. So how much voltage do we have if we have 1.5 times 2? 3 volts, that's correct. So we have 3 volts of electricity that's going through here. But I have 3 bulbs, whereas this one, circuit was 1. So I'm going to go ahead and connect, and let's see what happens to these 3 bulbs. You ready? 1, 2, ta-da! Look at that science happen. Isn't that wonderful? Now let's pretend that this is our particular type of Christmas lights. Well, what happens if one actually burns out? What's going to happen to the remainder of the lights? Go ahead now and make your prediction. So, what do you think? If I were to take this bulb out, what's going to happen to it? Let's find out. Oh my goodness. They all went out. No! What are we going to do? Reminds you of something? Reminds me too. Christmas light bulbs must be definitely in a series circuit. Well, series circuit means that each of the bulbs are all connected on one closed circuit. And by closed circuit means that everything is connected. Now, if there was an open circuit, that means then that one of these wires would not be connected, and therefore nothing could light. So what could we do to solve this problem so we don't go bananas again with all of our Christmas lights? Aha! Here's an idea. Are you ready to see? It's called parallel. Say parallel. That's right, I hear you. Parallel circuits. As you see, it's a completely different connection altogether as in that of the series circuit. Here's a series circuit, and here's a parallel. Big difference. And what is the difference you see? Is that each one of these has its own complete circuit. So then, what is your prediction of what will be when I connect, because right now it's open, when I make this a closed circuit? Go ahead and write that down. Okay, we're back. So let's see what happens when we're going to connect. 1, 2, 3. Look, they're both working together, lighting the light bulb. And as you see, they have pretty much the same intensity of light. So why is this called parallel, you may ask? Well, it's kind of like train tracks, because you have parallel lines going from one equidistance to the other. And it helps to be able to create this own circuit. So just as what we conducted when I took the bulb out, do you think that when I take this bulb out, the other light will stop? Make your prediction now. Okay, here we go. I'm taking the bulb out. Oh my goodness, the whole bulb, and what's happening? Our Christmas lights are still lighting. All right, wonderful. So, parallel, you say, is the way to go? I would have to agree. Absolutely. So, looking at the difference between these, of course, shows the difference of series and parallel. Now, great electrical engineers who help to be able to determine, as well as electricians, because where would we be without electrical engineers and electricians? In the dark, you're right. Anyway, I wanted to ask you this question. Looking at these two particular type of real models, let's pan over and see about the different types of diagrams then. So we have letter A, we have one diagram, and we have letter B, another diagram. Now I'd like to point out that this symbol here represents a battery, and the circle represents a bulb. So for letter A, how many batteries do we have? You're right, uno, one only. And how many bulbs? Tres, three. And what about letter B? How many batteries do we have? We have uno, one battery. And how many bulbs? Dos, two bulbs. So the question today is to ask, which one of these diagrams represents a parallel circuit and a series circuit? That's a good question. So which letter represents with A? Is A series or parallel? Go ahead at this time and make that notation in your science journal. So Luigi, which do you think is a parallel circuit? Well, I think he's saying letter B. Could it be a parallel circuit? Remember, what do we think of when parallel? That's right, both of these wires are parallel to one another, and that the bulbs are in sequence, one after another, but yet they have their own separate circle. So what is the letter B, Luigi? We would say it is parallel. So therefore the letter A is going to be series, because the bulbs are all on the same circuit. Wow, we've learned a lot so far today. Wow, we've gone through a lot of great information all about electricity. And, another thought is, well, where can we find electricity in nature? Well, Luigi knows about man-made because he is man-made. But where can we find electricity in nature? It's almost like a lightning strike. Well, wait a minute. You're right. It is a lightning strike. Electricity can be found in lightning bolts and other areas. What about fireflies? That's in nature too. So I challenge you to think of and look around. Where else can you find electricity, both man-made and natural? But I also want to have some fun with you too, just a bit. So, we're talking about closed circuit, open circuit. And so here we have batteries and we also have some circuitry. We got to put this together in order for something to work. So I'm going to start connecting. This is called a switch. A switch can be either on or off. Where else can you find a switch? Oh, you're right. The light switch in your house. Wonderful. Okay, so I'm going to go ahead and this is a motor. And as I had initially started out this conversation about making things light up and making things move, this is one of those instances. So as you see, I have a complete, what do you call it? Circuit. That's right. Okay, so what's going to happen then when I put this on and I'm going to press my switch? Are you ready? Here we go. Whoa, look at that. Oh my goodness, it really made this move. And what is it that you say? It is, oh hi Rocky, you wanted to say too? That's right. It's electricity. Isn't that fun? You want to do that again? I know I do too. Here we go. Oh my goodness, how fun is that? But my question is to you, what would happen if we change the electrical current to go a different direction? So what could I do? Well, at this point, let's change this because right now it's from a positive to a negative, and let's reverse it from a negative to a positive. Oh, I know! I'm so excited too. Let's see. What would happen with this, you say? Do you think it's going to go up in the air? All right. Nothing happened. But I did feel something different. Oh, wait a minute. It's a fan. Oh, how cool is that? We got 2 in 1. Just to show you that electricity, that's right, Rocky, can be used in different ways. Hi there. Okay, so I have a question for you for today. Is the fact of I have a magnet. What do you think is going to happen to this magnet when I wand over the paper clips? You're right. Let's find out. 1, 2, 3. Oh my gosh, I was able to collect them all. I'm the collector of all the paper clips. This is pretty cool, isn't it though? All right, on the count of 2, we're gonna see if I can release all the paper clips at the same time, just like I picked them back up. You ready? 1, 2, release. Okay, I said release. Release. I said release. Release. Okay, what's going on here? Someone give me a trick on this magnet. No, not really, because that's actually the physical property of a magnet, is that it attracts to metals. But does it attract to all metals? Only ferrous metals. Say ferrous metals. That's right, ferrous metals are attracted to magnets that have iron. Ferrous is iron. I say ferrous, you say iron. Ferrous, 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 that's right. Okay, so My other question is there a magnet out in this world that actually can do the same thing that this magnet does, but it can also release what it picked up, unlike what you just saw here? Well, what is that called, you say? An electromagnet. That's right. Oh, yay. So let me talk to you about you can create your own electromagnet. I have wire that you've seen that we've used before. And what do we have here? It's a nail. Correct. This is a nail. And I coiled the wire around it. This has about 25 coils. Can you see? What do you see about the spaces of the coil? Right. Are they close apart or are they separated? They're separated. So I'm going to attach my wire to the battery and let's see if we can create an electromagnet. Well, electromagnet, what does that mean? Well, there's electricity running through to the point that, well, could we pick up any paper clips? Let's find out, shall we? Almost. Maybe. Maybe not. I'm not able to pick up any paper clips with this so far. Wow. Oh, look, we have one. Success. But can we do better than that? Let's find out. Well, let's see here. I do have another battery that we could use. Now, what is the difference between this coil and this coil? You're right. Even though this nail has about twice the amount of coils, they are closer to one another. So do you think that would actually make a big difference? How close the coils are? Perhaps. Now let me ask you this. When it says electromagnet, what are we involving in an electromagnet? It's electricity in a magnet. How cool is that? So let's find out if we can pick up any much more of the paper clips than that of what we had for the first one. Are you ready? Here we go. The trial and the truth. Oh my goodness. We picked up so much more. But how did that happen? Well, have you ever seen an electromagnet in the junkyard where you have this huge magnet and it can pick up a lot of metal and then it can disperse it and displace it and it does something special to release it? Does anyone know what happens to be able to release? Well, we would call that a switch. If we would have a switch on here, we would turn it off and we could turn it on. But the question is, well, but why is this still hanging on? Well, what did we say at the very beginning of this lesson? Is that electricity is made up of electrons. And the electrons are all lining up on the coils in line and so much creating magnetism, electromagnetism. Therefore, being attracted, as we said, just as the magnet was to metal, so now is the electromagnet. How cool is that? So it has been a great opportunity to be able to spend some time with you as an electrifying lesson. I hope it was for you to be. I want you to know and remember this, just as Luigi would want you to be. Always be positive. Keep strong. And no, good, better, best, never let it rest till the good gets better and the better gets best. Look who joined us back. Oh, don't be so shy, Rocky. I know electricity is so much fun. Don't you think so too? Wonderful. Well, we've had so much fun, but we're almost over having conversations with electricity, but we couldn't finish without knowing this information. Well, what do you think this is? You're right, it's a magnet. So my question is, what's going to happen to a magnet when I have paper clips and I wand over the paper clips?